Hello everyone and welcome to this video on how we can quickly develop an AI-based virtual sensor for position sensing using a reference example from Motor Control Blockset. So we will explore how virtual sensors can be integrated into motor control by going through the complete workflow. Now, before diving into the workflow, let's take a look at where we will end it. So here you can see an AI-based virtual sensor performing real-time position estimation. And this demonstration showcases how the trained neural network enables sensorless PMSM speed control, providing reliable position estimation without the need for a physical sensor. So we have seen how an AI-driven virtual sensor estimates rotor position to control the speed of a motor in real time. But sensorless estimation isn't always straightforward. And that is where Motor Control Blockset comes to your help. So Motor Control Blockset provides pre-built blocks for achieving sensorless control as shown here. And this includes popular techniques like flux observer, sliding mode observer, extended EMF observer, as well as the AI-based virtual sensor, which we will go through with this video. All these sensors which we can see here are basically effective for the medium to high speed operation of PMSMs. However, when the motor is starting up, we have nearly zero back EMF, and that is where we need some kind of a startup technique to move forward with these sensorless techniques. And there's different options available with Motor Control Blockset for these as well. So overall, to support your sensorless implementation, Motor Control Blockset offers pre-built blocks and reference examples which showcase how these blocks can be integrated, thus helping you jumpstart your implementation. So in this video, we will focus on AI-driven approach using neural network, showcasing how data-driven models can be used for position estimation. Now let's take a quick look at the workflow to understand how each step builds towards AI-driven sensorless control. So we begin with the position sensor-based field-oriented control model for collecting the data for training the neural network. So this is what we'll have in such a case, which is the basic field-oriented control used as an initial setup to gather the training data. So multiple simulations are run in Simulink utilizing this pre-configured model. The collected data is then used to train a neural network for rotor position estimation. Now this entire process is automated through a live script which we will be going through, which basically streamlines your execution and guides you through each step. Once trained, the network is exported to Simulink and then you would have the AI-based position estimation as shown, thus eliminating the need for a physical sensor. We can then move on to validate the performance of this virtual sensor with simulation and then proceed to generate code from the same model and later deploy it onto our target hardware for validation purpose. So with that, let's move on to the demonstration by exploring the reference example in detail. So this is the example with Motor Control Blockset which we were talking about. Let's open this up in Simulink. So you can see that this example basically opens up a live script which gives you details about the entire example. And all the files related to this example are available over here for you to go through. The example basically guides you through the workflow to train, simulate and implement a neural network so as to create a virtual sensor for estimating rotor position. So it includes a model which we will be using for generating the data to train the neural network. And you can open up this model from here. So you can see that this is basically field-oriented control architecture which is implemented over here. And you can see the control subsystem and the plan subsystem. Inside the plan subsystem, you have a lumped permanent magnet synchronous motor as you can see and an average inverter which is driving the motor. Coming back, you can see the multi-loop control architecture for field-oriented control wherein there is an outer speed loop and an inner current loop. So as seen here in the current loop, we also have a selection for which position sensing would be used. So this could be from the encoder as we discussed to generate the training data. And once it is done, you could switch over to the position estimated through the neural network to validate the simulation. So this selection is done from over here. And with that information, we can just move on to run the simulation and view the results in the data inspector. So in the data inspector, we can select the signals which we want to view. We can see how the speed feedback is accurately tracking the speed reference with the encoder in place. Let's move on to the remaining part of the live script. Now, how do we generate the training data? So this is also covered in the live script. So in the model itself, we have provisions to sweep speed as well as torque through which we would be operating. And then we have this capturing of the signals of interest, as you can see here, like V alpha, V beta, I alpha, I beta, and theta values. And to do this, we basically have divided the speed ranges into two areas. To cover this in more detail, let's have a look over here. So you can see that the 0 to low speed range, we basically have a constant torque, as this is seen commonly in most applications. And here we collect about 100 cycles of data. Whereas in the low to high speed range, we are varying the torque throughout the range possible, and we are again collecting the data. So this totals to about 1100 simulations being run, and we then move on to extract one stable electrical cycle for each of these operating points. So in the live script, you can see all of this activity is basically provided with functions, and you just need to run this part of the script to start capturing the training data in simulation environment.
And we can see how the speed and torque references sweep across the ranges. This keeps on running as we discussed for 1100 simulations, and since these many simulations take a good amount of time, so I am speeding it up to jump ahead. We can have a look at the results in the data inspector then. And as you can see, you can select different signals. Like, for example, I've selected currents in the DQ frame, and you can see the responses along with the speed response and how they follow the references here for this particular run. And since this complete data is available, we move back to the live script. Now from here, we need to extract one electrical cycle information from all the different simulations which we went through. The utility function here on running returns the refined data which gets stored to these objects. Then we can concatenate this extracted data which would be processed later for training and validation process. And again, as you can see, the script includes all these functions and can be run from here. Post this, we can then move on to the processing part. So here, as we discussed, the data is split into training and validation. And you can see that the data split is basically 70% of the data is being used for training, whereas the remaining 15% is used for validation and the last 15% as testing data. And we can do all of this by running this part of the script. And then we can move to the training part with the available data. So we are using the nonlinear autoregressive neural network to estimate the rotor position as we discussed. And the architecture for this can be seen in this next section, that is the train and the test neural network part. So the code to develop this part is basically given here, which we can run, and it is used to train, test, and validate the network. So this would basically open up a training progress monitor, which is available with the Deep Learning Toolbox. So as the name suggests, it is basically used to track the training progress and view information during the training. So what you can see over here is the training and validation losses over the entire set of training iterations. We can also view the mean squared error value for the trained ARNN network. And as seen, it is basically in the range of e to the power minus 6, which indicates that the network is trained successfully. Now that we have trained the neural network, the next step is to export the trained ARNN. And for this, we use the export network to Simulink function from the Deep Learning Toolbox to export the trained ARNN network to the Simulink layers block, and it creates the ARNN network, which we would be using for simulation and code generation. So we basically need to copy this from here and paste it in the model which we were working with. So I'm just opening up the model and going to the neural network observer where this would be pasted. And all of the steps which I mentioned is also described clearly in the live script for you to refer to. And now that we have the neural network in place, let's validate it first with simulation and then move on to code generation. So for validation, we would be running the simulation first with encoder in place, and then we switch over to the neural network based estimation, and we would basically compare the results. for both the cases to understand the effectiveness of the implemented neural network. So I'm just checking the speed feedback response in comparison to the speed reference for both the cases, and you can see that the neural network is able to replicate what the encoder has done, thus proving the effectiveness of the network. So now that we are done, we can move on to deploying it to test it on hardware as well. And all we need to do is click build, deploy, and start. And now this is possible because the model is created for the supported hardware with everything configured in the model. So here you can see that the hardware input peripherals like ADCs, EQEPs are configured. Similarly, you can also configure the output peripherals like PWMs, which can be found over here. So hence we can just click build, deploy and start. And this starts the code generation process and then automatically deploys the code onto the hardware. So this here is enabled with embedded coder and C2000 microcontroller block set, which enables us to configure those peripherals for this TIC2000 device which we are working on. And it's not just C2000 devices which we can work on. So MathWorks has support for many popular microcontrollers and FPGAs, so you can generate driver code for any of these controllers, thus automating process of generating driver code for hardware, saving time and effort in the development process. So with that, we come back to continue with the code generation. And once that is done, you have your code generation report available. So let's have a look at the code generation report and module side by side. So here you have code generation report. You can go through the code generated. And as you can see, it is accessible as well as readable. So now that our code has been generated and deployed, we can move on to validation by opening the host module. So a quick glimpse at the hardware setup before we proceed to the demonstration. So we have a dyno setup where the test motor is mechanically coupled to the second motor that acts as a load for validation and testing. As you can see, both these motors are controlled with its own MCU and inverter setup. So we hence have two host models set up accordingly to control these motors. These host models serve as an interface between the target hardware and our PCs, allowing us to monitor and control the motor's operation in real time within the MathWorks environment. With this understanding, let's move on to the demonstration. So here we have the host models for both the motor under test and the dyno motor which is used for loading it. So let's run the host models and initiate it by clicking the start button. So here we see 0% load is being applied. With that, let's start running the motor at 500 RPM, which is the reference speed. So you can see how the speed feedback is accurately tracking the reference speed. Let's increase the load torque slightly. So right now we have 5% of the rated torque applied as load. With that, let's increase the speed reference to move from open loop mode to the closed loop sensorless mode, which is the area we are interested to validate properly. So now we are in the closed loop sensorless mode. Let's increase the load torque and see how the system responds to it. So you can see we are slowly increasing the load torque, and right now it's at 30% of the rated torque. We can go further ahead and see how the motor speed is still tracking the reference. We can increase the motor's reference speed and see how it responds at this percentage of the load torque which is being applied here. Coming back to 2000 RPM, let's further increase the load torque and see the performance. So we can see even at 60% or 70% of the rated torque, the speed feedback is accurately tracking the speed reference. So with such approaches, you can test and validate your control systems. And once you're happy, you can reduce the load and slow down the motor and then observe the results as well. So right now we are at 1500 RPM at 10% load torque. We reduce it further to 500 RPM, which is again the open loop mode where we begin with. Once you are done with the testing process, you can stop the host models and have a look at the results. So in the first scope, we can see how the motor under test is responding to step changes in speed reference. And on the scope at the bottom, you can see the changes in load torque done for the validation purpose. You can also zoom into the results to have a better look. So this is a response of the motor to a step change in speed, and we can see how the motor is able to accurately track the reference speed. Similarly, we can have a look at the IQ reference and IQ feedback as well. So based on the torque percentage inputs we are giving, we were having changes in the IQ reference and the IQ feedback, how accurately it is tracking it. And you can see the changes in the speed feedback based on the load torque being applied. So there's slight dips when there is increase in the load as expected, but you can see how it track the reference speed even when it is loaded. So this helps to validate how accurately our control system works together. And with that, we have come to the end of this demo. So just some more numbers to help you understand this solution better. So here's the code footprint for this algorithm, and the time taken to execute this virtual sensor part as seen is just 4.2 microsecond in the 50 microsecond current control loop. And we can see that the error between the estimated position to the actual position is within 1%. So with that, we have come to the end of this video, and summarizing, we went through this workflow wherein we demonstrated how to develop an AI-based virtual sensor for motor position estimation, thus replacing physical sensors with a data-driven approach. And we started from data generation, moved through neural network training, and finally deployed and validated the model on hardware. We did this on a TIC 2000 microcontroller in this video, but if you wanted to try it out on an STM32 microcontroller, the reference example is available for that as well, making it easy to get to your STM32 microcontrollers. Thus, with these reference examples from Motor Control Blockset, you now have a structured path from data collection to deployment and validation, enabling you to implement AI-driven sensorless control for your motor control applications. Thank you.